In this video, I'm going to analyze this RL circuit using phasor analysis, and specifically we're going to calculate the current IS here, which is the current from the power supply through the two elements. So it's the same current flowing throughout the loop. We're going to represent the supply voltage as a phasor, capital VS. That'll be the reference phasor, so it's a complex number but with angle 0, so it's basically got 0 imaginary part. The three things we're trying to calculate are the RMS current, IRMS, the peak current, and the phase angle of the current. That's going to be relative to our reference phasor VS. So essentially this will be the angle, the phase angle, or the phase difference between the current and the voltage in the circuit. So I'm going to just start on a blank piece of paper and I'll just show what the steps are going to be, and then I'm going to do them in Octave first, and then I'm going to simulate the circuit in LTspice so we can compare the actual waveforms with the results of the phasor analysis. So the circuit that we're given is as follows. It's got an inductor, a resistor, and they're both connected to this power supply. So our power supply is going to be represented by a phasor VS. We've got our current here, IS. So the S subscript here is just for supply, because this is the supply voltage and it's the current that's coming from the power supply, IS. Let's just call these R and L. And basically the steps that we're going to follow are, we're going to convert everything in the circuit into an impedance. Well, sorry, I should say the resistance and the inductance are going to be converted into impedances. So I'm just going to represent those impedances using these kind of generic rectangular symbols here. So I'll just call this one Z1 and I'll call this one Z2. You could call them ZR and ZL or whatever, but I'm just going to treat them really generically here as Z1 and Z2. Now the formulae that you use to convert resistors, inductors and capacitors into impedances are as follows. The impedance of a resistor is just equal to its resistance. The impedance of an inductor is equal to J omega L, where omega is the angular frequency in radians per second and J is the square root of -1. And for a capacitor, which of course we don't have in this circuit, but I'll just include it here for completeness, that'll be 1 over J omega C. So as I say, J is the square root of -1. Omega is the angular frequency, so that's just 2 pi times the frequency in hertz. So these are three very important formulae, and whenever you're going to apply phasor analysis to a circuit, the first thing you're going to need to do is convert these type of elements into impedances, and these are the formulae that are going to allow you to do that. So once we've got our circuit in this form, there's IS, VS, so these are phasors, so VS and IS are complex values. We can just analyze this the same way we would if these were two resistors. Basically we just combine the two impedances in series and then use Ohm's law to solve for the current. So the circuit will become a very simple circuit. Z3 is going to be the series combination of the two of these, and then of course it's very straightforward to use Ohm's law to calculate IS. So we've got Z1 is just going to be equal to R. That's using this formula here to convert that resistor into an impedance. I mean, there is no difference for a resistor between its impedance value and its original resistance. Z2 is J omega L. I should have said in this case the frequency originally given here was 50 hertz, so this is F equals 50 hertz. Omega therefore is equal to 2 pi times 50, so that's approximately equal to 314 radians per second. Just rounded to a whole number there, but it's close to that. And as I say, J is the square root of -1. So that's how we calculate Z1 and Z2. Z3 is just the sum of Z1 and Z2. because they're in series. And we can calculate IS then just using Ohm's law. So there's our voltage phasor Vs. So Ohm's law here would be Vs is equal to Is times the total impedance, which is Z3. But if I rearrange this, I get Is is equal to Vs divided by Z3. So that's how we're going to calculate IS. Once we get IS, which won't take long, a couple of things we can get from there. IS is a complex number, so it has magnitude and it also has an angle. The magnitude of IS is I RMS, so that's the RMS magnitude of the current. The angle of IS is basically telling us how far ahead or behind the voltage waveform the current is leading or lagging. So in this case it's going to be the current will lag behind the voltage because it's an inductive circuit. So IS is going to be the angle, the phase angle difference between the current and the voltage. And we also know that the peak voltage, the peak current, I should say I peak, is going to be equal to root 2 times I RMS. So we're going to be able to get the three things that we need once we have IS. These are the three things we're asked for. So in Octave, what I'm going to do is I'm going to create an M file to solve this problem. So every time you write a program, whether it's an M file or any other type of program, you should begin with some comments to explain what the purpose of the program is, to identify your name and the date that it was last updated, that type of information. So I'm going to include that here. What will we call this? Let's call it RL circuit. Just go to RL circuit.m, written by Ted Burke, 9th of March 2021. And the purpose of this is just to calculate the current in an RL circuit using phasor analysis. Okay, so the first thing I'm going to define here is the frequency, and I'm going to create a variable f to store it. So f is going to be equal to 50. That's given to us in the original problem statement. We can also then therefore straight away calculate the angular frequency. Now there is no omega on my keyboard, so I'm using a lowercase w, but that is in place of the lowercase omega from the Greek alphabet. So 2 pi f. We can also put in our component values for R and L. So R was given as 40 ohms. L was given as 50 millihenries. So that's times 10 to the minus 3. So the way that we write that in Octave is e minus 3. So it's 50 times 10 to the minus 3. So one of the things in phasor analysis is that the whole analysis is going to be contingent on the frequency. So if you change the frequency, you would have to rerun the analysis because all the impedances will change. So that's why I set the frequency first. If you were to change the frequency of the supply in this problem, you'd have to go back and change this variable. And then all of the resulting calculations after that would change as a result. So we've put in R and L. I can calculate the impedances. So Z1 was my resistor, so I'm just going to say Z1 equals R. Z2 was the inductor, so it's J times omega times L. Then what else did I have here? So combine impedances in series. So this is the resistor and the inductor into a single equivalent impedance, which I'm going to call Z3. So let's just Z1 equals Z1 plus Z2. And then use Ohm's law to calculate the current. Now what I forgot to do up here as well was to define my supply voltage. So this is going to be our reference phasor. So in this case, Vs for this one was given as 24 volts RMS. So the magnitude of the phasor is always going to be the RMS magnitude of the waveform that it represents. So in this case, it's the reference phasor, so it has 0 angle. So we can just say Vs equals 24. So then down here, I'm going to apply the formula that I had on the page there. So Is is going to be equal to Vs divided by the total impedance Z3. And I just want to print out the three things that we were asked to find there, which are the magnitude of Is. So I'm going to assign them to variables, but it's really just that I want to actually get them to display on the screen when I run this M file. So I'm going to call this I RMS is going to be the magnitude of Is. So we can get that using the absolute value function. The absolute value of a complex number just gives us the magnitude of the complex number. So that's I RMS. I peak is going to be root 2 times that. So root 2 times I RMS. So that gives us the maximum current value that the waveform reaches at its very peak, or at its very trough it reaches minus that value. And finally then the angle. So this, I'll just store this in a variable called I phase. So this is the phase, sorry, what have I done there? This is the phase difference between this current phasor and the reference phasor, which is the voltage Vs. So I phase is angle of Is. And that is going to be an angle in radians. So it's going to give us the phase in radians. So that's more or less everything. I'm going to save this file so that I can run it, and I'm just going to save it as RL circuit. So I actually already seem to have a file there called that, so I'm just going to replace whatever was there before. Okay, so I've got my M file, RL circuit.m. So to run that, I'm going to return to the command window and just type the name of the M file. Now you don't need to type in the .m extension, you just give the name up to but not including the file extension. And you'll see it stepping through all of the instructions that I put in there. So it's assigning values into the different variables, calculating the impedances, and so on. And then it finally gets to this point where it calculates the complex number that represents our current, Is, that's our current phasor. And then we calculate the RMS and peak values, and also the phase angle. And you can see here that the phase angle, as we expect, is a negative number. So it's about minus 1/3 of a radian, I mean, roughly speaking. So we'll be expecting the current to lag behind the voltage by maybe about 20 degrees. So we'll see if that's the case when we simulate it in LTspice. So that's the phasor analysis part complete. We now are going to switch to LTspice and simulate the circuit there. So okay, so here we are in LTspice. I'm going to create a new circuit. So go to new schematic from the file menu, and I'll put in the voltage supply first. So I'm going to select component from the toolbar here, and I'll type volt here to search for the voltage element, and click OK. So this is our voltage supply in the circuit, and so click once to drop one of them onto the canvas, and then I press escape to get rid of the voltage supply. Now I'm going to select the resistor. So click on, there's a button on the toolbar for resistor, so I can drop that down here. Again, click once to drop a resistor and then press escape to get rid of the resistor dropper. Finally, inductor. So drop in the inductor here. Click once to drop one and then press escape. I'm going to use the pen tool to join up the lines in the circuit there. So click once, click, click and click, click and click, 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 click and click. So you have to be careful to click the lines exactly on the terminals of the components to make sure that the lines actually connect up. One thing that I haven't put in here yet, but I should put in, is a ground as well, just to specify which node in the circuit is the ground node. So I'm going to put that in at the bottom here, and then I'll just use the pen tool to connect it to that bottom node. So click and click. Okay, so we're nearly there. I'm just going to unzoom the canvas to make sure everything is visible. I still have to set the values for these different components, so maybe we'll begin with the resistor. So if I right click on that, I can type in the resistance in ohms, which for this circuit is 40. Press OK. For the inductor, the value is 50 millihenries, so I can type in 50M. It'll understand all the standard SI prefixes, so I can just type 50M and it'll put it into millihenries. And then for the voltage supply, so in this case I'm going to select advanced, and I'm going to specify that this is a sine voltage source, and I need to specify some parameters here. So the DC offset, is 0. The amplitude here is going to be, remind me, what is it? 24 volts. I'll have to check. I'm not actually sure whether I specify peak or RMS amplitude here, but we'll see when I plot the waveform, and I can come back and change this if I have it wrong. The frequency is 50 Hertz. And the number of cycles, I suppose we might run this for, maybe I can just leave that blank actually. Let's try that. So I'm going to move that over to the side a little bit just to neaten things up here. So move that over to there. Now I need to specify what type of simulation that I'm going to run. So if you click on the little running man up here, that's not what you'd normally press to trigger a fresh simulation, but when you click it the first time, it'll ask you what type of simulation you want to do. So the type that I'm going to do here is a transient analysis, because I want to see the actual waveforms that are being generated in the circuit here. So I suppose I might run it for, let's say we'll run it for 1 second. But I'm just going to, I want to get 2 full cycles of the waveforms. So if the frequency is 50 Hertz, that means the period of the waveform, the time it takes to complete 1 cycle, would be 20 milliseconds. So 2 full cycles would be 40 milliseconds. Now the thing is, I don't want to take the data from the very beginning of the simulation, because the waveforms won't have actually settled into steady state at that point. I want to give them a good few cycles to fully settle down before I actually record them. So I'm actually going to take the last 40 milliseconds of the simulation. So I'm only going to begin recording at 0.96 milliseconds. So just 40 milliseconds before the simulation ends. I'm going to leave the rest of that blank for now, and hopefully that'll be enough. So you can see as soon as I press OK there that the simulation actually runs, and it brings up a blank graph here, but we haven't specified which waveforms we actually want to observe yet. So when you hover it over the circuit diagram down here, you'll see you're offered 2 different types of tools. So when you hover over an element, you'll see the current loop measurement tool, and when you hover over a node, you see a voltage probe tool. So in this case, I'm going to plot the voltage waveform at the top node. That's the supply voltage, and you can see there's two cycles of the supply voltage. As I suspected there, it's actually, when I specified 24 volts, it they have set that as the peak voltage rather than the RMS voltage. So before I go on any further, I think I'm going to calculate what the peak voltage should be, and I'm going to put that in instead so that I really do have an RMS voltage of 24. So I'll just use Octave to do that. I'll just say square root of 2 times 24. So 33.941 is what I should have set the voltage to here. So I'm going to change that from 24 to, what did I say there? 33.941. So that's the peak voltage, but that's equivalent to an RMS voltage of 24. I'm going to run the simulation again. Yeah, so now you can see the voltage waveform is a bit bigger. The RMS voltage is 24 now, but the peak voltage is higher. So the current that we're interested in is the current through the power supply here, or we could measure it through these. So I think I'm going to measure it through one of these things here. And you can see that the current magnitude is displayed on the vertical axis on the right hand side of the graph here. And you can see it's going up to about 800 milliamps and down to about minus 800 milliamps. But you can also see, as we were expecting, that it is lagging behind the voltage waveform by maybe about 20 degrees. And you could go in and measure that more accurately, but it looks to me like it's more or less in agreement with our calculation. Let's just check that magnitude though. So the current peak value should be 789 milliamps, and that looks very close to what we have there. So you can see it's just short of 800 milliamps. So this looks good to me. So that's basically it. That's probably a good place to stop the video.